Hi, my name is James Walker, and I'm going to present my research on active charge control using an electron beam and ultraviolet light source. So a little bit of background and motivation. Interactions with the plasma environment of space can lead to spacecraft charging. Essentially, uh, energetic electrons, protons, and ions can impact the surface of a spacecraft, stick, and lead to charge accumulating on the spacecraft charging. Um, And this can become significant when you have two charged spacecraft in close proximity to each other. As they approach each other, you will get electrostatic forces and torques generated between them that can alter the spacecraft's relative motion. Now, a lot of research that has gone into spacecraft charging is focused on um, modeling or mitigating these electrostatic forces and torques. However, we actually want to use them in this project. The electrostatic tractor is a concept proposed for removal of large debris objects from geostationary space uh, using these electrostatic forces and torques. The idea, which is shown in the image, uh, is you have a servicing spacecraft approach a debris object with an opposing charge. Because you have this opposing charge, you have an attractive force between them. And using this attractive force, you can actually tug the debris object to a graveyard orbit. Now, the key to this is the opposing charges. You have to be able to generate uh, a positive charge on one, a negative charge on the other, and know that each of the spacecraft is positively and negatively charged. And we can achieve this using an electron gun. So a servicer equipped with a higher energy electron gun approaches the debris object and aims the electron gun at the object, applying a negative current to the debris object, decreasing its electrostatic potential. Now, because the servicer spacecraft is emitting electrons, it's actually losing this negative charge. Therefore, it has a positive current on the spacecraft, increasing its electrostatic charge. And the result is a positively charged servicer and a negatively charged debris object. And this attractive force, which we refer to as the electrostatic tractor, is generated. Now, in order to actually implement this electrostatic tractor technique, we have to be able to control this electrostatic force between the two objects. And we can do this by controlling the potentials on each of the objects. The electrostatic potential of the object is directly related to the charge of the object, which is directly related to the Coulomb force generated between them. And that is the focus of this project, controlling a target's electrostatic potential. Now we do this using active charge control. In this presentation, active charge control refers to generating a desired electrostatic potential on a target object. And now to do this, you need three major things. The first is a measure of the target's potential. And we achieve this using an electrostatic voltmeter to just directly measure the target's electrostatic potential. The others are a negative current and a positive current. The electron beam applies a negative current to the target, while ultraviolet lights are used for the positive current. Now, the ultraviolet lights are able to do this through the photoelectric effect, where high energy photons impact a target surface and can be absorbed by the surface electrons. If enough energy is transferred from the photon to the electron, it will be excited and can be emitted from the target surface. With electrons leaving the target surface, you have a positive current. This project is focusing on combining these three components to make a feedback control that allows us to control a target's electrostatic potential. This research involves experimental results, and so we conduct vacuum chamber experiments. The image on the left shows the target object that's being irradiated by the electron gun. It consists of a gold-plated copper disc, a Faraday cup, and a UV detector. The copper disc is the target that we're actually interested in. The Faraday cup and the UV detector are included so we can get estimations of the number of respective particles impacting the surface of the target. However, it was found that the electron beam actually affected the results gathered by the UV detector, so we didn't get any usable data from it, and as such, they are not included in this project. The image on the right is the actual setup that we use inside the vacuum chamber. You can see the three UV lights that are used to induce the photoelectric effect. The electron gun is actually inside the wall of the chamber, so you can't actually see it. And then you have the Trek probe, which is the electrostatic voltmeter used to measure the target's potential. Now, the electrostatic voltmeter is 3 millimeters from the target surface. So while it is very close, it is not touching. So the disk that we're using as our target is electrically isolated from the surrounding area. So for all intents and purposes, it is floating. The control that we apply in this project is applied to the grid of the electron gun. So within the electron gun is a conducting grid that when a potential is put across it, it restricts the number of electrons being emitted from the gun. Therefore, it controls the current emitted from the gun. By controlling this current, we control the current that is impacting the target and therefore the target's potential. So onto our results. We used a proportional and derivative control that uses a measurement of the target's potential. And we applied it to a variety of charging scenarios. Each scenario consists of a different beam energy and a different desired final potential. So for instance, the first one is we use an 8 kilo electron volt beam to induce a negative 500 volt potential on the target. And what we found, and some of the results are shown in the images here, is that for each of the charging scenarios presented here, we were able to find gains that resulted in the target potential converging to the desired electrostatic potential. And as well, it was able to converge relatively quickly. So each of the results shown here, it was able to converge within 2 minutes. And it was able to maintain this potential for the duration of the experiment. So what we're showing here is that we are actively controlling and inducing the desired potential of a target, which was a major goal of this project. Another important factor is the error at steady state. So across each of the charging scenarios presented here, we didn't reach any error greater than 3%. And that occurred for the 10 kilo electron volt beam inducing a negative 500 volt potential. We got a 3% error, meaning at steady state, there are oscillations around the negative 500 volts of about 15 volts, which is very good for these results. It's a very low error relative to the final potential that we're inducing. One thing I want to talk a little bit are the vacuum ultraviolet lights used in this experiment. No control is applied to the lights. They can only be turned off and on. So we wanted to look at what happens if we leave them off. What this means is that there is no major positive current acting on the target without these lights on. And what we found is that just charging the object up to negative 4,000 volts and just letting it discharge, you can see that with the lights on, it takes about 2 minutes to fully discharge. And without the lights on, it takes over an hour and the target doesn't fully discharge. The image on the left shows the results of this experiment, but over different time frames. So without the lights, it takes a significant period of time for a target to discharge. Now, what does this mean in terms of control? So we applied the PD controller to our target without the UV lights on, and what we found is that the result is very sensitive to overshoots. So what happens is the object charges up, and once it reaches that negative 500 volt potential, the electron beam shuts off. But because it has reached a potential that is now in magnitude larger than that 500 volts, it has to discharge back down to 500. And because there is no significant positive current happening on being applied to that object, it takes a significant period of time. So the images below shows on top it's a negative 8 kilo electron volt beam, and on the bottom is a negative 10 kilo electron volt beam used to induce a negative 500 volt potential on the target. The image on the bottom, we have a overshoot of 100 volts, and it takes over 5 minutes for the target to discharge even close to the desired target potential. It doesn't actually reach it over the time frame shown here. But what this means is that without the VUV lights, it will take a significant period of time for our system to reach a steady state. And even when it does, it will have large oscillations and deviations from and a large max error. So for our purposes to get results in a reasonable time frame and with high accuracy, we need to include these VUV lights. Now, in contrast, one thing we actually found while exploring this was that we can use the electron beam to actually induce a positive current. Now, this is due to secondary electrons. So similar to the photoelectric effect, when an electron impacts the surface of a target, it can transfer its energy to one of the surface electrons. And if enough energy is transferred, that surface electron will be emitted as a secondary electron. Now, what can happen is if there's some probability that more than one electron will be emitted per impacting electron. So if a higher energy electron impacts, it can excite multiple electrons, which then are emitted, meaning that you have more electrons leaving the target as are incoming, and you have a positive current on the target. And we found that throughout these experiments, we could actually induce this effect. We didn't look very deep into this yet because it wasn't the focus of the project. But what we found is that we can actually use this the second electron effect to apply these positive currents. What this means is that we might not actually need the VUV electrons to apply this positive current. We might be able to achieve it solely with the electron beam. Now, throughout this project, we only used current control to our electron beam. We only control the current being emitted to apply these techniques to a different charge scenario. We would have to also include electron beam energy control, which would require a different experimental setup. Future work for this project, we want to explore this electron beam energy control, but the other big step would be to apply remote sensing techniques to our controller. So throughout this project, we use an electrostatic voltmeter to measure the target's potential. Now, this electrostatic voltmeter has to be 3 millimeters away from the target to get an accurate measurement. Now, this is not realistic for an actual charging scenario in space, so we need to apply a different method for measuring the target's potential. In our lab, we have developed techniques for doing this, the secondary electron method and the X-ray method, and we can contactlessly, remotely sense a target's potential using a servicing spacecraft. But the big difference between these remote sense techniques and this electrostatic voltmeter is, while the electrostatic voltmeter gave us measurements on about 1 second time frames, the remote sensing techniques can take upwards of a minute to multiple minutes to actually get an accurate measurement. So with this increased time frame to get a measurement, it will significantly affect the effectiveness of the controller and additionally the controller that we use through this work. So we are going to look at applying these techniques and exploring them in use of active charge control. I'd like to give special acknowledgments to Ryan Hoffman and the SICL lab at AFRL for their assistance in this research. These are references used throughout the paper. And more information about these secondary electron method and X-ray methods for remote sensing are given on the website, as well as information on the electrostatic tractor. But with that, thank you for your time.